but definitely, there's going to be a lot of things you're going to need to ask me about that I consider like that.
Yeah.
I kind of knew that, and then when you ask them, like, oh yeah, they're not going to know how to recast this.
Yeah.
But now you do.
Unless I want to work on it here.
You can work on it here. I don't care.
And so I also need to change it to put out the unit as well. So like 5.00V.
Yep. We'll do that. Tell me everything you know about capacitors.
It blocks DC.
It blocks DC. It holds a charge. So capacitors hold charge on their plates. They hold energy in the electric field between the plates. So yeah, reminders, simple example. If I have a 5-volt battery, that means I'll have 5 volts across my capacitor. That means I'll have 0 current going through the circuit. And the other thing I can remind myself of is I am not sure. There we go. Charge over CV. So I can have charge over CV. That's my triangle, kind of like we do with Ohm's law. Or if you prefer, it is that the charge equals the capacitance times voltage. So Q, you got to watch out. Q is the charge measured in coulombs. C is the capacitance measured in, drum roll.
Farads.
Yes, farads, and almost always milli, micro, nano, pico. Usually milli and micro. They're not quite as bad as capacitors for small, but V is electric potential, or voltage, and volts. That's the easy one. You have V and V. So do be careful of your C's.
Who designed this?
And it's going to happenstance. We built this moving along. So just like a coulomb is a measure of charge that we came up before we knew anything about atoms. So it's not some like, nobody came up with, oh, it's so many electrons, or so, I mean, there are so many electrons in it, but it's nothing like that. It's just like a convenient measurement they came up with, and like, hey. Okay, but it's a lot better than trying to measure. I have something times 10 to the 20th electrons on this. It's like, no, charge. This is one of the few places we need it. So if I wanted to know the charge, Q, I would have to know the capacitance. Let's give ourselves a capacitance value. Let's make it easy. That's 1 microfarad. So I would take C times V, which is 1 microfarad, times 5 volts. So there are 5 micro coulombs on the plates of that capacitor. What that actually means is you have plus 5 microcoulombs on one side and minus 5 microcoulombs on the other. Capacitor's net charge is 0, but because there's a gap in there, they don't get to equalize ever. So it's polarized. It produces electric field between the two, and inside that electric field is a bunch of energy. You can disconnect your capacitor and carry it around as long as you don't short the two ends or connect them where they can drain. And in theory, the capacitor will have 5 microcoulombs on it a minute later, an hour later, a year later, a millennia later. In reality, of course, they're going to drain slowly, but There's some leakage between the plates through, you remember there's a dielectric in the middle? So there'll be some leakage through that, of course, even through the atmosphere or whatever. But they actually can hold, big capacitors can hold lethal charges on them for days or months after the last time you used, if you go to big power amps and stuff. So you discharge them first. Nothing we use in here in this class has got that much ability to hold a charge. Okay, so capacitors hold charge on their plates, hold energy. That's what they really do. Now, we have a couple of things we're going to talk about. First of all, series capacitors. Series capacitors have this wonderful equation. It's just like parallel resistors. Parallel capacitors have this wonderful equation. That's just like series resistors. So let's try that. Let's come over here. I'm actually going to do the parallel one first because it's easiest. All right, let's see. Let's say I've got a 12-volt battery. I've got 2 capacitors. I have a 1 microfarad. I have a 5 microfarad. If that's hooked up, what's my current? 0. What's my charge on this one? I'll call this capacitor 1, capacitor 2. Charge on the plates capacitor 1 is capacitor 1 times the voltage, which is 12 volts. So 1 microfarad times 12 volts is 12 microcoulombs on the plates. Twelve volts times 5 is 60 microcoulombs on that plate. So I've answered everything I can, right? They're in parallel. Parallel is parallel is parallel. Therefore, they all have the same voltage. No current DC flows through it. Boring. and I have charged the plates. All right, let's do series. Does this all seem familiar now? We covered it last semester, but we did it one day. So I'm going to do it basically one day this semester.
So would the capacitance measured then be 6 microfarads?
Yes.
Okay.
Thank you for asking that. I should have done it. So let's try this one. We'll actually have to do it solve this one. So let's take C1, which is 1 microfarad. C2, actually it's right, 1 microfarad down there. Just give myself space. It's 5 microfarad. Current 0. What's the voltage across each of them? I know it's going to sum to 12 volts, but I don't know how to get there without doing some calculations. So my total capacitance, 1 over 1 plus 1 over 5, that's 5 over 5, right? So I get a common denominator. I mean, you could just do this on your calculator, but 6 over 5. So total capacitance is 5/6 of a microfarad, which is, where's my calculator? I got it out earlier to do 2 to the 10th power. 5/6. 0.833333 microfarads. So I can now rewrite my circuit as 12 volts. Through a single capacitor, that's 0.833 microfarads. So the charge on the plates of the capacitor is 12 volts times. So I take 12 times 0.833 and end up with 10 microcoulombs. Okay. I'm hiding as much as I can behind the monitor. Good job. So now, here's the key to these. If you recall, this little thing here is a conductor, right? So charges can freely flow back and forth, but it's isolated from everything else. So this overall conductor from this plate through this wire to this plate has to be neutrally charged. Which means when I fully charge up this plate, those will be equal and opposite charges. That means over here, I have to get exactly the same charge down here, right? Since this thing is isolated, it has to have the same negative charge here as positive charge there. So I have them in series. Everybody has the exact same charge. So guess what all those charges are? Minus 10 microcoulombs, plus 10 microcoulombs, and this is minus 10, plus 10. There we go. Now I can go back and find the voltages. So voltage across capacitor 1 is the charge over capacitor 1, which is 10 microcoulombs over 1 microfarad is 10 volts. And across 2, and yes, they do add to 12 volts. You probably could kind of reason this one out with nice even numbers like 1 and 5, but that's how you do these. So if I ask you, pretty sure in your homework you have a couple with series and parallel, go through and calculate the series parallel total capacitance. And if I have something like, can I erase this? And if I have something like this, how would I work it? Well, just like my series and parallel resistors, except for make sure you use the right equation because they're reversed. But have that on your equation sheet when you get the final exam. So these two capacitors are in series, right? So I use the series equation. So what would that total capacitance be for those?
1 microfarad.
Yeah, 1 microfarad. I made this one easy. 2 1 microfarads in parallel.
2 microfarads.
Yeah, 2 microfarads. Actually, I didn't make it. Let's go back and change this. Just to make life easy. That way we can do it all at the board. So if I wanted to find all the charges on these, I could go back. I gotta tell you, I don't have to do a whole lot of calculation here to look at this and go. Those are each 5 volts. I can find the charge.
Right, yeah.
That means this one is 5 volts. That means it's 5 volts there. Up here, this is 5 volts. That's 5 volts. And these are each 2.5 volts. Okay. If you didn't have nice numbers like this, you'd have to go find the charges and do it like we did before. But you can build it back up. Find the total capacitance. All right, not done. RC circuits. You have that whole time constant, tau, which is RC. Tau. It's Greek T. So here's the thing in time. With time, typically small t is the variable. Like how far am I in time? It's a thing we usually don't like to work because it's math to get a specific time. I don't care about that one time. I want to look at the bigger thing. Capital T is the period. I go through one total cycle. So I already used my little t and my big T. I need another T, I go for tau. That's probably a pretty standard issue, by the way. You run out of English letters, you go for Greek.
Yeah, there's a lot of Greek in this class.
Yes. That's kind of a classic scientific thing, because back in the day, people doing science mostly did it as a hobby on the side, because they were aristocrats who learned Greek and Latin as part of their education. But they weren't expected to do things like science. They just did it during the summer.
My Arduino is doomed to talk with the potentiometer forever.
Yep.
I think it's still going over there, even though the computer has locked itself out.
Right. Actually, if you disconnect it and you connect the power supply to the Arduino, it should still run. So it has a little separate power on there. You can plug like in and use like a 9-volt battery or.
And I have a wall adapter in it.
Yeah. Okay, let's go on here. If I have an RC circuit, so we did this last semester. Let's make that 100. I think we did 100 kilo ohm, 1 microfarad. Maybe it was a 10. Maybe it was 100 microfarad. Yeah, we'll do this. So when I do a single pole double throw, I always ask that, right? Because it has 2 connections, one swing. If I'm up here, if I'm down here, it drains, right? Because it can drain through the resistor. Then I swing it up here, and what happens? It starts charging. Now, one of the things it didn't say on this capacitor yet is no instant change in voltage. So I had all those capacitors by themselves, circuits. We're just like, okay, it's hooked up. This is what it does. But if I have a resistor here, even if the resistor is very small and just the wire, it takes some time. If it's just the wire, it's probably so short your human eyes and senses cannot track it. But it does not literally go from 0 to 10 volt. It goes from 0 to 10 volts. It just might be in like, micro or nanoseconds or something. We can track it with a computer setup. But here, I look and I go, okay, what is tau? So tau is RC, which is 100 kilo ohms times 1 microfarad. So that's 100,000 times 1 times 10 to the minus 6. And I get 0.1 seconds. Okay, first of all, my time constant, it does not take me 0.1 seconds to go from 0 to 10 volts. Do you remember how many it takes, roughly?
Like 5 time constant.
5, yeah. So if I were to look at this, my voltage on my capacitor is going to start at 0.
Isn't it like a set percentage?
Yes.
Okay.
It will end up here at the source voltage, so in this case 10 volts. If we look here, I'll give you the big ones. At 3 time constants, so 0.3 seconds here, it will be at 95%. So, okay, I guess I can manage that 9.5 volts. At 5 time constants, it is going to be at 99.3, but let's call it 99. So it'll be 9.9 volts, 99%. So yes, there was a thing that says, look this up in your text and don't the number of time constants. So 1 time constant, 2, 3, 4, 5. You want the little graph. The percentage charged. So let me do this off the top of my head. So let's see. I believe this is 86. Is that right? This is 95. This is like 97 or 98, 99. And down here is 60 something. Okay. Pull them off the chart. Don't trust my memory. But they're somewhere in that range. There's a whole calculation if you're interested in it, but if you ever wanted to know what e to the power stuff does for you, it's that graph. E to the minus t divided by tau. What? Times the 5 voltage.
That, cause like, it's like a graph.
That would produce this graph. You know what E is? E is the natural number. So
Yeah,
pi is the most common irrational number in the universe, right? Because it relates the circumference of a circle, well, it relates really the diameter of a circle to the area. After it is E, the natural number, which is how fast things naturally rise or how fast 1 minus that would be. Actually, let's see, if I put 0 in, it starts at 1. Yeah, that one's actually wrong for this anyways. This one would start at maximum and go down. So this one would look like this. If you had this one, all you have to do is subtract E. Just subtract 1. I'm sorry, subtract it from 1. So it's everything naturally decaying or growth. Radioactive decay, the rate at which a capacitor charges or discharges, the rates that populations naturally grow or go away.
Like that, just based off time constants.
What's that?
Like all those like non-electrical related things.
Yeah,
They're all the same percentages, just different time constants.
they would be. So this time constant's a way to do it without plugging into this thing. Because here I can plug in any numbers, I could end up with like, 1.623 time constants. Or I could use it to find exactly how much time. We don't want to do this, plug it into this thing, so we just look at these time constants and then get close. So, and you have a little graph that shows you the charging and discharging. So, if I were to take a look at this, if I look at time in this, at 0, 0.3 seconds, 0.5 seconds, sometimes I'll say like a long time, like say a minute. The voltage across the capacitor, voltage across the resistor, and I'm going to squeeze right there with the current. Voltage across the capacitor is 0, hasn't any time to charge, right? This is when you close the switch. That means all 5 volts across the resistor. Because they'll still have to sum, oh, I'm sorry, 10 volts. So I got 7 by 5. So these two have to sum to 10 volts. So how much current do I have? Well, I have 10 volts divided by 100,000. So 0.0001, I could go 0.1 milliamp, but it's going to shrink, so I'm going to get 100 microamps. Is that okay? So we started at 100 microamps. After 3 seconds, I have 3 time constants, so this has gone up to 9.5 volts, right? Which means I have 0.5 volts there. So I take 0.5 divided by 100,000. And I'm down to 5 microamps. And after 5 time constants, I'm at 9.9 volts across the capacitor, so 0.1 volts across the resistor, which means 0.1 divided by 100,000. You probably know what this is already, right? 1 microamp. Is it clear where I'm getting those? After a minute, I'm going to say, hey, that's 10 volts, that's 0 volts, that's 0 current. It asymptotically approaches. Remember that math term, asymptotically? Means it approaches but never quite reaches it, but it reaches it. Just too fun. All right, so if you looked at the voltage across the resistor, it would start at 10 volts and it would go down like that. So those two are always going to sum to 10 volts. And my current's going to drop. Now, after this is fully charged, it ends up at 10 volts, 0 volts, no current, just sits there, nothing's happening. I flip the switch down here and what happens? Well, that's 10 volts. Capacitor voltage can't immediately change because it's directly related to all the charge on the plates. But my resistor voltage can. So I have to have 10 volts around here, so I'm dropping 10 volts. So I have a current that's flowing that direction. What's happening? It's taking current, taking charge from this side of the plate, moving to that side, slowly making it neutral. Okay, we will say current flows through the capacitor here frequently. We know actually no charge jumps from one side, one plate to the other capacitor. It flows through the circuit to the other plate. If charge is jumping from one plate to the other, and that gap between, it's not really a capacitor anymore. It's not holding charge. It's a spark plug. Essentially, that's what a spark plug is. Except for instead of having a big wide plate, it has a little sharp point on the end. You build up a bunch of charge up to the point the electric field's higher than that can be supported by air and arcs. And then gasoline fumes in there and they explode. That's it. You have the same thing, day like today. Clouds build up a huge charge. Clouds act as a capacitor, clouds versus Earth. They build up a huge charge. When it builds big enough, it will release as a static discharge called light. Yeah, you don't think of clouds being a capacitor. They can.
How many farads is one cloud?
I have no clue. Look it up. I'm not sure you even rate it as farads. I think you just rate the charge as being held in there. But yeah, I don't know. And the guy was actually observing this morning teaches meteorology, so maybe I should have asked him. All right, so if this starts, I'll do the same thing. This will be 10 volts. That's 10 volts. So guess what my current is? 100 microamps. After 0.3 seconds, I will have dropped 95% of the voltage to 0.5 volts. My resistor voltage is 0.5 volts, right? Since I'm not connected to the source, these two have to be the same because this is the source I have of energy in the system now. But unlike a battery that has a chemical inside that can keep charging it, this doesn't. So it just, as it drains, it just drains. So my current now is dropped to 5 microamps. After another 0.2 of a second, I'm all the way down to 0.1 volt here, 0.1 volt there, 1 microamp. So notice, when I'm charging it, this voltage is increasing, while this one decreases, and the current decreases. When I'm discharging, these two voltages are identical, so don't get caught up. I see a lot of students do that. Oh, well now my capacitor is going down, so my resistor is going up. No, it's not, because you're not connected to the battery. So you're discharging, taking the energy out of the system. Yeah. So a lot of people will make that mistake. They'll go, oh, hey, I just flipped the direction. But you're not hooked to the battery now, so your total voltage of these two is no longer equal to the battery voltage. Now it's equal to each other because this is the source and that's the load. Okay, questions on capacitors? I'm going to talk about inductors now, so I'm not done. I just want to stop, but I'm going to erase the board. Start a new video.